Good morning, all my colleagues and principal present in Capacity Building Program, Regional Teacher Training Center, Branch. The purpose of this workshop is to share our teaching techniques with our colleagues so that we can transfer our knowledge to our children in the classroom in an effective way. So today my topic is hybridizations and molecular concept. First we will try to understand what is hybridizations and why the concept of hybridization is required. Okay, uh, in order to understand what is the concept of hybridizations and birth of hybridization, let us consider the formation of a methane molecule on the basis of valence bond theory or orbital overlapping theory. We all know the hybridization state of carbon, the atomic number of carbon is 6, its electronic configuration is 1s2, 2s2, 2p2. This is the ground state electronic configurations. In ground state, it has only 2 half-filled atomic orbital in its valence shell. Therefore, according to valence bond theory, its covalency should be 2. But we all know carbon is tetracovalent. In order to explain the tetracovalency of carbon, we consider the excited state electronic configuration. In excited state, one electron gets unpaired and enter into 2p orbit. So now we have 1, 2, 3, 4 atomic orbitals. And the energy required for the excitation of electron from lower energy level to higher energy level will be compensated by the energy released during the bond formations. Okay. Now let us consider the formation of methane molecule. According to simple valency theory or valence bond theory, the bond is formed by overlapping of atomic orbitals. Like in this case, there are 4 hydrogen atoms having electronic configuration 1s1, means having 1 electron in its 1s orbital. And according to this concept, the s orbital of carbon should overlap with s orbital of hydrogen and p orbital should overlap with s orbital of hydrogen to form 4 covalent bond between carbon and hydrogen. Now, according to this concept, one bond is formed by overlapping of ss atomic orbital and the remaining 3 bonds are formed by overlapping of s and p orbitals. Therefore, the one bond should be different from the remaining 3 bonds. The bond length of this bond should be different from the remaining 3 bonds because these 3 are formed by overlapping of s orbital of hydrogen and p orbital of carbon. But experimentally, it is found that all the carbon hydrogen bond having equal bond length 109 picometer and equal bond energy. Their bond energy are also equal. They have equal bond energy and equal bond length, as well as the HCH bond angle is found to be 109 degree 28 minutes. the equivalency of the 4CH bond and the bond angle of HCH is 109 degree 28 minutes cannot be explained by valence bond theory. So here the concept of hybridization was introduced to explain the equal bond energy and equal bond length of CH bond in methane as well as the bond angle in methane, right? And this concept was introduced by a great scientist, Pauli. Who introduced the concept of hybridization? Pauli. Now, what is the concept of hybridizations? What is the concept of hybridizations? See, according to Pauling concept, the pure atomic orbitals will not overlap with s orbital of hydrogen to form covalent bond. These 4 atomic orbital, 1 s atomic orbital and 3 p atomic orbital first undergo intermixing to form 4 new orbitals. These are called sp3 hybrid orbitals. All these 4 sp3 hybrid orbitals having equal energy and identical shape. Equal energy and identical shape. And these 4 atomic orbitals, sp3 hybrid orbitals, having tetrahedral geometry. Okay, because these hybrid orbitals repel each other and they will arrange themselves in such a way that there is a minimum repulsions. So they will arrange themselves at an angle of 109 degree 28 minutes. 109 degree 28 minutes in this way. Suppose in this room carbon atom is in the center and the 4 sp3 hybrid orbitals are directed towards the 4 alternate corners. Okay, so they have tetrahedral arrangement in this way. 1, 2, 3, 4. This is the 3-dimensional figure. 1, 2, 3 and then 4. sp3, sp3, sp3. So these 4 sp3 hybrid orbitals are formed. These sp3 hybrid orbitals having the character of both s and p orbitals. Okay, it has 75% character of p orbitals and only 25% character of s orbital. But now these orbitals having equal energy and identical shape. So now when these atomic orbitals will overlap with half-filled atomic orbital or s orbital of hydrogen, we get 4 sigma bond. We get 4 sigma. Okay. The s orbital of one s orbital half-filled, one s orbital overlap with half-filled sp3 hybrid orbital of hydrogen to form 4 sigma bond. In this way. Now, since these orbitals having tetrahedral arrangement, therefore, in methane also these 4 covalent bonds, CH bond, having tetrahedral symmetry, right? These having tetrahedral symmetry in this way. And the angle is 109 degree 28 minutes. We can draw it in this way. And all the 4 bonds are formed by the overlapping of the orbitals having same energy and identical shape. Therefore, these four bonds having equal bond energy and equal bond length. So this is the birth of hybridization. So hybridization is a purely theoretical concept which was introduced to explain the equivalency of bond and the structure of the molecule, shape of the molecule, okay, which cannot be explained on the basis of simple valence bond theory, right? Now, what is hybridization? So hybridization is the intermixing of pure atomic orbitals of an atom having slightly different energy to give a set of new orbitals having equal energy and identical shape, right? So the main points of hybridizations are: the orbitals taking part in hybridizations must have nearly equal energy and identical shape, okay. The number of hybrid orbitals formed is equal to the number of orbitals undergoing intermixing, and all the hybrid orbitals will have same energy and identical shape, right? Okay. And the most important thing, these hybridization state will decide the geometry of the molecule, because these hybrid orbitals repel each other and they arrange themselves in the space in such a way that there is a minimum repulsions among them, okay. So this is the concept of hybridizations. Here we will discuss how the concept of hybridizations is helpful to know the geometry of the molecule or shape of the molecule or shape of the simple ions, okay. Here I will also give a formula to know the to predict the hybridization state of the central atom. So let us see how to predict the hybridization state. And so you can write predicting the hybrid state of central atom, the hybrid state of central atom in simple molecule or ions, simple molecule or ion. And also we will discuss some molecular geometry, right? So I am giving a formula first. X equal to SA plus 1 by 2 G minus V plus minus. First we should try to understand what is X, what is SA. SA is number of surrounding atoms. G, what is G? Number of valence electron of free central atom. What is V? V is number of monovalent atoms attached to central atom, or double of divalent atoms attached to central atom, right? And A is charge on ion. If there is a negative charge, we will add, and if there is a positive charge, we will subtract. And x equal to number of hybrid orbitals. If the value of x equal to 2, the hybridization state will be sp. X equal to 3, sp2, x equal to 4 sp3, x equal to 5 sp3d, not sp4, because there are only 3 p orbitals. X equal to 6 sp3d. Right. Now let us consider the formations of some molecule, and we will predict the hybridization state and shape of the molecule. Let us consider one example first. Formation of XeF2 molecule. What is XeF2? It is xenon difluoride. In this case, what will the value of X? Number of surrounding atoms 2 plus 1 by 2. Number of valence electron in xenon 8, minus fluorine is monovalent atom. Therefore, there are 2 monovalent atoms attached to the central atom. Its value is 2. There is no charge. So it is equal to 2 plus 8 minus 2, 6 by 2, 3 equal to 5. It represents the lone pair and it represents the bond pair. Okay. It means, what will the hybridization state of xenon? It should be sp3d. And the 5 sp3d hybrid orbitals having which type of arrangement? It has a trigonal bipyramidal arrangement. Trigonal bipyramidal arrangement like this. This is the trigonal bipyramidal arrangement. 3 orbitals will lie in the same plane at an angle of 120 degree, and they are directed towards the 3 corners of an equilateral triangle, and the remaining 2 are perpendicular to these 3. Right? Now, let us see how the bonding takes place. How the bonding takes place in case of xenon. Xenon 54, its outermost electronic configuration will be 5s to 5p6. Here there is no half-filled atomic orbital, therefore its covalency should be 0. But we know here it shows dicovalency. In order to explain it, we consider the excited state electronic configuration. In excited state, one electron from here get excited to higher d orbital. Higher d orbital. Now, one s orbital, 3 p orbital, and 1 d orbital. This is the first excited state electronic configuration of xenon. Will undergo intermixing to form 1, 2, 3, 4, 5 sp3d hybrid orbitals. What will the arrangement of these 5 sp3d hybrid orbitals? It is trigonal bipyramidal arrangement like this. Xenon 1, 2, 3, 4, 5. These 3 are in the same plane at an angle of 120 degree, and these are perpendicular to the plane. Now it contains 3 lone pairs. The lone pair should be kept in such a way that there should be minimum repulsions among them. Therefore, we should keep lone pair in equatorial position. These are called equatorial positions. So these 3 orbitals containing lone pair of electrons, and the remaining 2 half-filled atomic orbitals, sp3d hybrid orbitals, will overlap with half-filled p orbital of fluorine. If you write the electronic configuration of fluorine, it is 1s2, 2s2, 2p5. So this half-filled p orbital will overlap with half-filled sp3d hybrid orbital of xenon. Now you can see this is the shape of XeF. its shape is linear shape. Okay, all these three atoms will lie in the same plane in a straight line, so it has a linear shape, right? Now let us consider the formation of a special case, the formation of phosphate ion. Phosphate ion, PO4 3 minus ion. What will be the hybridization state of phosphorus in phosphate ion? Okay, see, here in case of phosphorus, X equal to number of surrounding atom 4 plus 1 by 2, 5 number of valence electron in phosphorus, 5 in free state, minus oxygen is a divalent, therefore it will become 5, 4 to the 8, and there are 3 negative charges, here we put plus 4 plus 0 equal to 4, means there is no lone pair first, and the hybridization state of phosphorus is sp3. So it should have a tetrahedral geometry, and the shape of the molecule, the arrangement of hybrid orbitals will be tetrahedral, and the shape of molecule will also be tetrahedral in this case. Okay. Let us try to understand it, to feel it, how the bonding takes place. See, this is phosphorus, atomic number 15, its electronic configuration is 1s2, 2s2, 2p6, 3h2, 3p3. This is the ground state electronic configuration. In excited state, one electron from s orbital gets excited to d orbital. Now it has 1, 2, 3, 4, 5 orbitals. But out of 5, only the 4 orbitals will undergo intermixing to form sp3 hybrid orbitals. Okay, why not this? Because the hybridization explains the geometry of the ions or the species. Here, this species is tetrahedral, so the hybridization state should be sp3, and this d orbitals will not take part in hybridizations. Now, how the formations of bond take place? Let us see. This is phosphorus having 4 sp3 hybrid orbitals, sp3, 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 and one pure d orbital. One pure d orbital. Now, in phosphate, PO4 3 minus ion, we have 1, 2, 3, 4 oxygen atom. Out of 4, there are 3 O minus ion and 1 O. You know the electronic configuration of O. Atomic number is 8, 1s2, 2s2, 2p4. In oxygen atom, we have 2 half-filled atomic orbitals. So here we write first oxygen atom, which has, okay, we take first O minus ion. In O minus ion, there will be 5 electrons, so it is like this. Okay. 1, 2, 3, 4, 5. Now here also we have O minus ion. 1, 2, 3, 1, 2, 3, 4, 5. These are O minus ion, and there is one oxygen atom. 1, 2, 3, 4. Now, how the bonding takes place? The sp3 hybrid orbitals will overlap with half-filled p orbital of each oxygen in this way to form 4 sigma bond. As the arrangement of sp3 hybrid orbital is tetrahedral, therefore the arrangement of these sigma bond will also be tetrahedral. 1, 2, 3, 4. Right? Now O, 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 out of these three are O minus I and 1 is O. Now this p orbital of oxygen will overlap with d orbitals of phosphorus sidewise, resulting into the formation of pi bond. This is called d pi bond. This is the concept of d pi p bond, because this bond is formed by the overlapping of d orbital of phosphorus. So this will be the geometry of phosphate. Okay, it has a tetrahedral geometry. Here this bond is d pi bond. Is it clear? Now let us consider one more example. The one more example is of nitrate ion, NO3 minus ion. NO3 minus ion. This is called nitrate ion. In nitrate ion, this is the nitrogen atom. Okay. First we calculate x. X will be equal to 3 plus 1 by 2, 5 minus 6 plus 1. Is it clear? 3 surrounding atom, 5 number of valence electron. Oxygen is a divalent, therefore 3 to the 6 plus 1. Now it is equal to 3 plus 5 plus 1, 6 minus 6. So 0 is equal to 3. There is no lone pair. So the arrangement of hybrid orbitals and the shape of this species will be same. This ion will be same. Now let us try to understand how the formations of bond take place. This is the nitrogen atom. We all know atomic number 7, electronic configuration 1s2, 2s2, 2p, 3. In this case, the hybridization state is sp2. Therefore, one s orbital and 2 p orbital only undergo intermixing to form 3 sp2 hybrid orbital. 1 p orbital will remain unhybridized. Right. Now let us see how the bonding takes place in nitrate ion. This is nitrogen. sp2, 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 and this is a pure pure. Right. Now, in nitrate, there are 3 oxygen. One is O minus ion. So O minus ion having electronic configurations 2s2, 2p5. 1, 2, 3, 4, 5. Oxygen, it has only 1, 2, 3, 4. And one more oxygen atom having electronic configurations 1s, 2s2, 2p, like this. Now, this half-filled p orbital will overlap with half-filled sp2 hybrid orbitals of nitrogen to form sigma bond. Here also half-filled sigma bond. And what will happen? How these oxygen atom will form bond with nitrogen. Okay, let us try to understand. It is assumed that these electrons will undergo pairing with each other. After pairing, this orbital will become vacant. So the fulfilled orbital of nitrogen will overlap with empty orbital of oxygen to form a sigma bond. In this way, the nitrogen atom forms 3 sigma bond. Since the hybridization state of nitrogen is sp2, the 3 sp2 hybrid orbitals having trigonal planar arrangement, therefore these 3 bonds will lie in a plane at an angle of 120 degree. One bond with O minus I and the remaining 2 are with. Now, this oxygen atom contains one more half-filled p orbital. It will overlap with p orbital of nitrogen to form p pi p pi r. This is p pi. And this is the geometry of nitrate ion. Sometimes we show this bond by an arrow because here the bond is formed by overlapping of fulfilled orbital with empty orbital of oxygen. Therefore, this is a type of dative bond. Okay, there is no difference between the dative bond and the single covalent bond once the bond is formed. So this is the geometry of nitrate ion. Okay, and it can also show resonance, So on the basis of it has a trigonal planar geometry, trigonal plane. We can explain the geometry of simple molecule or ion on the basis of hybridizations. Thank you very much.